Right now, beneath the quiet farmland that stretches across the border of France and Switzerland, a machine the size of a city is attempting something extraordinary. Deep underground, far from cameras and headlines, the Large Hadron Collider is not just colliding protons for academic curiosity, it is probing the earliest fraction of a second after the Big Bang, searching for a particle that, if found, would overturn everything we believe about magnetism, energy, and the structure of reality itself. For centuries, our understanding of magnets has been simple and absolute. Every magnet has two poles, north and south. Break one in half, and you do not isolate a single pole. Instead, you create two smaller magnets, each with its own north and south. This symmetry appears unbreakable. It holds true in school experiments and in the quantum world. Even electrons behave like tiny bar magnets, always carrying both poles. The universe, it seems, does not allow a lone magnetic charge to exist. But physicists at CERN are searching for exactly that, a magnetic monopole, a particle with only one magnetic pole, no counterpart, no symmetry, just a single isolated magnetic charge. If such a particle exists, it would challenge one of the deepest assumptions in physics. It would mean that magnetic symmetry is not a fundamental rule, but a condition that can be broken. And that discovery would not simply adjust our textbooks, it would rewrite them. The interest in monopoles is not just theoretical. The implications are practical and they are enormous. Advanced quantum field theories suggest that a magnetic monopole could act as a powerful catalyst at the subatomic level. Specifically, it might trigger proton decay. Protons, the stable building blocks of atomic nuclei, are believed to have extremely long lifetimes. Yet certain grand unified theories predict that under the right conditions, they can decay into lighter particles, releasing energy in the process. If a monopole can reliably trigger that decay, the result would be the most efficient energy conversion process ever conceived. Complete mass-to-energy conversion, not a fraction of a percent, like current nuclear fission, not less than 1%, like the fusion reactions that power the sundae, but potentially 100%. To put that in perspective, today's nuclear reactors extract only a tiny portion of the energy stored in atomic nuclei. Even stellar fusion converts less than 1% of mass into usable energy. A monopole-based system, in theory, could convert all of it. A small amount of ordinary matter could produce energy on a scale that dwarfs fossil fuels, fission, and even fusion. This is why the search matters. A single confirmed monopole could open the door to reactors that generate vast amounts of clean energy without radioactive waste. In principle, almost any material could become fuel. The global energy landscape would change overnight. But energy is only part of the story. The existence of monopoles would also confirm that the four fundamental forces of nature were once unified. At the moment of the Big Bang, gravity, electromagnetism, and the strong and weak nuclear forces are believed to have been one single force. Over time, as the universe cooled, they separated. A monopole would be a surviving relic from that unified era, a fossil from the earliest moment of cosmic history. Evidence for such relics has been hinted at in the cosmic microwave background radiation, the faint afterglow of the Big Bang. Yet no direct detection has ever been confirmed. That is why specialized experiments at CERN, including the Modal detector, are designed specifically to capture the unique signature of a monopole. Unlike ordinary particles, which leave subtle traces, a monopole would leave an intense, highly ionizing track as it passed through detector material. If that signature appears, it would not just confirm a particle, it would confirm that our universe is deeper and more unified than we currently understand. And that possibility is exactly why the stakes are so high, and why the next phase of this search could redefine humanity's future. That possibility is exactly why the next phase of this search has moved from theoretical debate to active pursuit. At CERN, the focus is no longer just on smashing particles together at higher energies. It is on catching something that, according to conventional wisdom, should not exist at all. Inside the tunnels of the Large Hadron Collider, protons are accelerated to speeds just below the speed of light and forced into head-on collisions. These impacts recreate conditions similar to those that existed a fraction of a second after the Big Bang. Temperatures soar, densities spike, and for an instant, the universe behaves the way it did at its beginning. In that brief window, rare and exotic particles can form. Among them, scientists hope, could be the magnetic monopole. To detect it, researchers rely on highly specialized instruments, including the Monopole experiment, which is designed specifically to look for highly ionizing particles. Unlike other detectors that analyze energy sprays and particle jets, Monopole uses plastic tracking materials and magnetic trapping volumes. If a monopole passes through, it would not go unnoticed. Its magnetic charge would tear through matter with a strength far greater than ordinary particles, leaving a permanent and unmistakable track. The signal would be clear. It would not resemble background noise. It would not look like a minor anomaly. It would stand out. And that clarity is important, because the implications are too significant for ambiguity. If even a single monopole is captured, it would confirm predictions made by grand unified theories. These theories propose that at extremely high energies, the electromagnetic force and the strong and weak nuclear forces merge into one unified interaction. A monopole is not just another particle. It is a leftover fragment from that unified era. In other words, it would be physical evidence that the forces governing our universe were once a single, elegant system. That realization alone would reshape modern physics. But beyond theory, the technological implications are what make this search so closely watched. One concept gaining attention is the idea of a monopole-catalyzed reactor. According to the Kalin-Rubakov effect, a magnetic monopole could induce proton decay without being consumed in the process. It would act like a catalyst, triggering reactions over and over again. Stable matter, which normally lasts longer than the age of the universe, could be converted directly into energy in a controlled way. The efficiency would be unmatched. Current nuclear fission extracts less than 1% of the mass energy stored in uranium. Even the fusion reactions inside stars convert only about 0.7% of mass into energy. A monopole-based reaction, in theory, could approach full conversion. The result would be a level of energy density beyond anything humanity has ever handled. A tiny amount of matter could power entire cities. The global demand for fossil fuels would disappear. Nuclear waste would no longer be part of the equation. Energy scarcity, one of the defining challenges of civilization, could end. It is not surprising that such potential draws attention beyond academic circles. The nation or consortium that first isolates and controls a monopole would gain an unprecedented technological advantage. Energy independence would become absolute. Infrastructure, transportation, water desalination, and planetary defense systems could all be transformed. But this is where caution enters the conversation. There is an ongoing debate among theoretical physicists about vacuum stability. Our universe exists in what may be a metastable state. The Higgs field, which gives particles their mass, could in theory transition to a lower energy configuration. If that happened, a bubble of new vacuum would expand at the speed of light, altering the laws of physics as it moved. Most calculations suggest this is extremely unlikely. Yet when you are dealing with energies that approach those of the early universe, even unlikely scenarios must be considered. Some researchers question whether isolating and manipulating a monopole could disturb the local vacuum state. To address these concerns, data from CERN experiments are carefully cross-checked with observations from gravitational wave observatories like LIGO. Any unusual disturbances in space-time would be monitored. So far, no evidence suggests instability, but the fact that such precautions exist shows how seriously the risks are taken. We are not simply hunting a particle, we are testing the limits of the vacuum itself. And as the collider increases its luminosity and pushes toward record-breaking energy levels, the search moves into a new phase. The question is no longer whether the monopole is mathematically possible. The question is whether we are ready for what happens if we find it. Because discovering a magnetic monopole would not just solve a physics puzzle, it would force us to rethink how the universe is built from the ground up. At its core, modern physics rests on two powerful frameworks. One is quantum mechanics, which explains the behavior of particles at the smallest scales. The other is general relativity, developed by Albert Einstein, which describes gravity and the large-scale structure of space-time. Both theories work extremely well in their own domains, yet they do not fully agree with each other. For decades, physicists have searched for a deeper theory that unites them. Magnetic monopoles are central to that search. Grand unified theories predict that when the universe was incredibly hot and dense, all fundamental forces were merged into a single interaction. As the cosmos expanded and cooled, symmetry broke, and the forces separated into gravity, electromagnetism, and the strong and weak nuclear forces. A monopole would be a remnant of that symmetry-breaking event, a stable object formed during the transition. If one is found, it confirms that the unification was real. It shows that the early universe passed through a phase where magnetic charge did not require a counterpart. That would be direct evidence that symmetry, as we know it, is not absolute. It can fracture. This matters because symmetry principles guide nearly every equation in particle physics. The Standard Model, our most successful framework for describing subatomic particles, depends on these symmetries. A confirmed monopole would reveal that the Standard Model is incomplete, not incorrect, but limited. It would point toward a broader structure underlying everything we see. There is also an important cosmological angle. During a period known as cosmic inflation, the universe expanded at an extraordinary rate. Some models predict that inflation diluted the density of monopoles, spreading them so thinly across space that only a few would remain within the observable universe. That could explain why they have never been detected directly. But dilution does not mean absence. If even one monopole is observed at the CERN facility, it proves they survived inflation. It means relics of the grand unified era still exist, and that would reshape our understanding of the early cosmos. The implications extend beyond theory into engineering. A monopole carries magnetic charge in isolation. This would change Maxwell's equations, which currently assume magnetic field lines form closed loops with no beginning or end. With monopoles, magnetic field lines could start or terminate at a point. That subtle change unlocks entirely new electromagnetic configurations. Some theoretical models suggest this could support advanced propulsion concepts, including space-time manipulation strategies. Ideas like the Alcubierre metric, which describe contracting space in front of a spacecraft and expanding it behind, require enormous energy densities. Today, those energy requirements seem impossible. But if monopole-catalyzed reactions provide near-total mass-to-energy conversion, the scale shifts dramatically. What once demanded planetary levels of energy might be reduced to the output of a compact reactor. This is where physics transitions into long-term strategy. With a reliable monopole-based power source, humanity would not just solve energy scarcity. It would unlock continuous high-density power for deep space missions. Interstellar travel, currently limited by propulsion constraints, would enter serious engineering discussion. The Kardashev scale, which measures a civilization's energy capacity, classifies a Type 1 civilization as one capable of harnessing the total energy output of its home planet. Humanity is not there yet. We use only a fraction of Earth's available energy. But monopole technology could accelerate that transition dramatically. At the same time, such power introduces geopolitical tension. The first group to isolate and control a monopole would possess unmatched energy capability. That advantage would influence global economics, defense systems, and infrastructure. It would shift the balance of power. This is why data emerging from the Large Hadron Collider is treated with such intensity. The search is scientific, but its consequences are strategic. As luminosity increases and collisions become more energetic, detectors grow more sensitive. The team is not just watching for new particles. They are looking for a track that cannot be mistaken, a signal that confirms the wall of magnetic symmetry has finally broken. And if that moment arrives, physics will not gradually adjust, it will pivot. Physics will not gradually adjust, it will pivot. And when it does, the shift will reach far beyond laboratories and lecture halls. A confirmed magnetic monopole would not sit quietly inside a research paper. It would move directly into the center of energy policy, global security, and long-term human survival. The reason is simple. Energy density defines civilization. Every major leap in human history has followed access to a more concentrated power source. Wood gave way to coal. Coal gave way to oil. Oil led to nuclear fission. Each step increased the amount of usable energy we could extract from matter, but even our most advanced reactors today barely tap into the true potential locked inside atoms. Nuclear fission converts less than 1% of mass into energy. Nuclear fusion, the process that powers stars, converts roughly 0.7%. Both are impressive compared to chemical fuels, yet both leave most of the atom's energy untouched. A monopole-catalyzed reaction changes that equation completely. According to the Kalin-Rubikoff effect, a magnetic monopole could trigger proton decay repeatedly without being consumed. It would function as a catalyst at the deepest level of matter. Instead of splitting heavy nuclei or fusing light ones, it would cause protons themselves to break apart, releasing their full mass as energy. That is as close to complete mass-to-energy conversion as physics allows. To understand the magnitude of this, imagine converting even a few grams of ordinary material into energy with near-total efficiency. The output would surpass the lifetime fuel supply of conventional reactors. Entire cities could operate for extended periods on what today seems like negligible amounts of matter. This is why the experimental work at CERN carries such weight. The search is not speculative curiosity. It is a practical exploration of whether this catalytic pathway is physically real. If successful, the world's energy systems would be redesigned. Fossil fuels would become obsolete. Traditional nuclear plants would be transitional technology. Renewable systems would remain valuable, but no longer essential for baseline supply. Clean, dense, and continuous power would redefine infrastructure planning. Desalination plants could operate at global scale, addressing water scarcity permanently. Industrial processes requiring extreme heat could run without carbon emissions. Planetary defense systems could be powered to deflect or vaporize incoming asteroids. Energy would stop being the limiting factor. However, the scale of this transformation brings serious risk considerations. One concern is vacuum metastability. Our universe may exist in a false vacuum, a local minimum energy state maintained by the Higgs. Under normal conditions, the probability of transitioning to a lower energy vacuum is effectively zero on human timescales. But when exploring physics near grand unified energies, even remote possibilities are studied carefully. Some theorists ask whether isolating and manipulating a monopole could disturb the local Higgs field configuration. If such a disturbance triggered a phase transition, a new vacuum state could form and expand at the speed of light, altering the constants of physics as it propagated. Most calculations suggest this scenario is extraordinarily unlikely. Still, the implications are so profound that monitoring systems are in place. Data from the LIGO and other instruments are cross-referenced with collider output to ensure no unexpected distortions in space-time occur. So far, no anomalies have appeared. The universe remains stable, but the fact that these safeguards exist underscores the seriousness of the investigation. Beyond energy and risk, monopoles also alter electromagnetic theory itself. Maxwell's equations currently describe magnetic field lines as continuous loops. With a monopole, those lines could begin or end at a point. This adjustment seems small, but mathematically it simplifies charge quantization and explains why electric charge appears in discrete units. In that sense, monopoles would not complicate physics, they would clarify it. As the Large Hadron Collider increases luminosity and extends its high-energy runs, researchers are not simply waiting for a rare particle, they are actively testing the durability of the Standard Model and probing the earliest conditions of cosmic history. If the detectors register the unmistakable ionization track of a monopole, the consequences will not unfold slowly. Governments, research institutions, and industry leaders will respond immediately, because at that moment the conversation will shift from whether monopoles exist to how they can be controlled safely and responsibly. And that shift could mark the beginning of a completely new era in human capability. And the moment control becomes the question, the stakes change completely. Discovering a magnetic monopole would be historic. Containing it would be revolutionary, because the true challenge is not detection, it is stability. A monopole, if produced at extreme energies, would not behave like an ordinary particle, it would carry an isolated magnetic charge, something never observed in nature under normal conditions. That charge would interact powerfully with surrounding magnetic fields, accelerating rapidly unless confined with precision. So the next phase after discovery would not be celebration, it would be engineering. Physicists have already outlined theoretical containment strategies. One approach involves superconducting magnetic traps capable of generating controlled field gradients. Another proposes layered cryogenic chambers to reduce kinetic energy and prevent unwanted interactions. These are not science fiction ideas. They are being quietly modeled in advanced research programs. If a monopole could be captured and stabilized, even briefly, experimental physics would enter uncharted territory. Scientists would test whether it truly catalyzes proton decay through the Kalin-Rubakov effect. They would measure its magnetic charge and compare it to the predictions made by Paul Dirac nearly a century ago. They would analyze how it interacts with quantum fields and whether it confirms grand unified theories that aim to merge the strong, weak, and electromagnetic forces. And if those experiments confirm theoretical predictions, the implications will reach far beyond one laboratory. The world's understanding of unification would sharpen. For decades, physicists have searched for a single framework connecting all fundamental forces. Gravity remains separated from the quantum realm, described by general relativity rather than the Standard Model. A verified monopole would serve as evidence that deeper symmetry once existed in the early universe, broken as temperatures cooled after the Big Bang. In other words, we would gain direct insight into the first fraction of a second after cosmic expansion began. Cosmology would adjust accordingly. Models of inflation would be refined. Predictions about relic particles from high-energy phase transitions would be revisited. observational data from space telescopes would be reanalyzed with new theoretical tools. Even astrophysics would feel the impact. Some scientists have speculated that monopoles could already exist in nature, drifting through interstellar space since the early universe. Experiments like those at CERN search for artificially produced versions, but large-scale detectors buried underground or suspended in Antarctic ice also monitor for cosmic relics. Facilities such as IceCube Neutrino Observatory and other deep space observatories analyze high-energy particle interactions for unusual ionization patterns that might indicate a passing monopole. So far, nothing conclusive has appeared, but limits are tightening. Sensitivity improves every year. If one were detected naturally, it would confirm that the early universe produced them in measurable quantities. That discovery alone would reshape cosmology. But let's return to Earth, where the most immediate consequences would unfold. Energy independence would become a solvable problem rather than a political debate. If monopole-catalyzed reactions prove viable and controllable, power generation would shift from extraction to conversion. The limiting factor would no longer be fuel supply, but containment design. This raises inevitable geopolitical questions. Who owns the technology? Who regulates it? Who ensures it is not weaponized? Any energy source capable of near-total mass-to-energy conversion carries dual-use potential. The same mechanism that powers cities could, in theory, release enormous destructive force if misused. International treaties governing nuclear materials would need expansion. Monitoring frameworks would require revision. Transparency would become critical. At the same time, access to abundant clean energy could reduce global tensions rooted in resource scarcity. Regions lacking fossil fuels would no longer depend on imports. Developing nations could industrialize without carbon emissions. The environmental impact would be transformative. Yet optimism must remain grounded. We are still at the detection stage. No confirmed monopole has been captured. No catalytic proton decay has been measured in a controlled setting. The experiments at the Large Hadron Collider continue, pushing luminosity higher, refining detection thresholds, filtering enormous volumes of collision data for anomalies that might last only fractions of a second. Most runs yield nothing unusual. But physics has always progressed through persistence.